Greetings, Earthlings. Now, I got a great question, which is when we're doing these mod problems and raising these numbers to various powers and checking their residues or what they're congruent to, mod whatever, it seems that we tend to get a lot of ones or negative ones, but basically ones. So I'm going to show you guys a few examples and show you how frequently we get these ones and then comment on what's going on. So for example, 4 to the 30th, if we want to know what that's congruent to mod 5, we might start hunting and just check that 4 is congruent to -1 because we could just subtract a 5. And from here, it's easy to raise -1 to a large power. So I'm not going to try to answer these questions. I'm just going to show you that in our quest to answer them, we're going to get a lot of ones. So there's a -1, which if we square that, in doing that, we're eventually basically going to get a 1. Now let's go to another problem, 7. So 7 squared, we could have actually made a 7 into a 2 mod 5, but oh well. I squared 7, so if we're looking for a pattern, so 7 squared is 49, and 49 is congruent to -1 because it's 1 away from 50. So now -1, that's another, I highlighted in red because again we're getting these ones or -1s. Same if we pick another two numbers like 13 and 9. We see, okay, 13 is congruent to -4 mod 9. Let's try squaring it because we want to see how far do we have to go till we get a 1 or -1. So instead of working with the 13, we're going to work with the -4. So I'm going to square the -4, get 16. 16, if you chop off a 9, is congruent to 7 mod 9. So now that's still not a 1, so let's try doing it again. So I'm going to cube the 13, but instead of using the 13, we're going to use the -4. So we're going to do -4 cubed, and we use our answer over here. So that's -4 squared. So it's -4 times -4 squared, which we said is 7. So that gets us -28. And if we add 27, which is a multiple of 9, we get -1. So again, we get a -1. The point is, very frequently, sooner or later, if we keep doing this, we're going to get a 1 or a -1. So you guys might wonder, will this always be the case, and why does this happen? So let's try another example. In this example, 4 is congruent to -2, but 4 squared is also congruent to -2. So this one's basically going to cycle and never hit -1. So that's just to show you guys, no, it will not always be the case. But why not? Notice there's a key property. The 4 and the 5, the 7, the 5, 13 and the 9, and then the 4 and the 6. So here, the greatest common factor of 4 and 6 is actually 2. So they're not relatively prime or co-prime. So the word relatively prime means they have no factors in common other than 1. It doesn't mean that the numbers themselves have to be prime. So neither 4 nor 6 is prime, and so their GCF would be 2, so therefore it's not 1. But here, the GCF of 13 and 9 is 1, so these two numbers are relatively prime. 9 is not a prime number, but it's prime relative to 13 because they have nothing in common. So, in cases where these two numbers, the base here and the mod, are relatively prime, we will eventually get -1s or 1s. Now, why is that? That's a more interesting story. So, well, let's first stop here, because here we can get stuck in a loop, right? And we may never hit the 1 or -1. So if they're not relatively prime, we're not guaranteed to get the 1s or -1s. So to understand what's going on here below, I've written out a few fractions. So we have 1/7, which as a decimal is going to be the repeating decimal 0.1428587, and then it continues 1428587 many times. Infinitely many times. Let's try 1 over 53, which will be 0.0188679245283. Anyway, that's 13 digits long, and it's going to cycle. So what does this have to do with this? Notice that we got 6 digits over here, and that's not an accident because if we're dividing 1 by 7, if you divide any number by 7, there are only so many possible remainders. The remainders are 0 through 6. Now, if we got a 0, this wouldn't be a repeating decimal. So other than 0, 1 through 6 gives us 6 possible remainders, and therefore it's not surprising that this is actually of length 6 before it starts to repeat. Now, it doesn't always have to be like the number of remainders, it could be less than that. And actually, if you guys want to explore this, because this is a whole can of worms, I encourage you to study this much further, which is Euler's Totient function, which measures how many prime numbers are less than the number. So for example, with 53, there are 52 numbers that are relatively prime to 53. So from 1 to 52, those are your 52 numbers. Now, 52 and 13 are related. 13 is actually a factor of 52. So if you're wondering why in the world is this a 13, how could we have predicted that, you would want to study this. And the 13 is related to this function of 53, which it happens to be 52. So I'll leave it at that. Now let's bring that back here. So if we're seeing what is 4 to this power divided by 5, there are only so many remainders when you're dividing by 5, right? There's a remainder of 0, 1, 2, 3, and 4, and same for the others. There are only so many possible remainders, so it's no surprise that if we keep multiplying numbers, we are going to go through all of our options. Like we may not go through all of them if the numbers are not relatively prime. We may start to cycle, or we're going to basically exhaust all our possible remainders, and once we've done that, we will start to repeat remainders. And that's what we're seeing here. So notice let's say for 13 and 9, we didn't get this -1 right away. It took us a few, like we had to square it, cube it, then we got our -1. Because there are only so many options, and we're basically going to exhaust all our possible remainders. So I'll leave it at that. Hopefully that gives you guys a glimpse. This is not a full explanation, so if you really want to understand this in depth, you should go study this. And let me know in the comments if you guys have questions or anything you'd like me to talk more about.